All right, back from break. Now, I just wanted to review very quickly what we've done. We're in chapter 27. We said chapter 27 is giving us kind of an introduction to magnetic fields and forces, and then we're going to start solving for magnetic force in particular. So these problems look like this. What they do is they go, okay, given a certain magnetic field that's already present, what kind of a force will that exert on current that's passing through that magnetic region? And so we looked at a couple of examples with currents running through. And so we wrote down what the formulas were, what formulas were going to be used. And we said this is, that's our go-to formula for calculating the force acting on a current going through a magnetic field. And we said an analogous formula that's actually more fundamental is to look at individual charges, and that's what we're going to do next. And so we've looked at the current. Let's come back and look at individual charges. So, oh, there it is. So the formula here says that the force acting on an individual charge, maybe this is a beam of electrons or it's a beam of protons that are being sent through a magnetic field. Maybe it's a mass spectrometer, which maybe you guys have used in some chemistry classes or something, to determine the mass of an object. You charge molecules and send them through magnetic fields. In any sense, they have a different right-hand rule than what I'm using. You're welcome to use theirs. You're welcome to use the one I'm introducing. You're welcome to use a different one if you've run across a different one and encountered it. But it's basically the same idea as before of if I have a positive charge going into a magnetic field, if Q is positive, then F will be in the direction of V cross B, and we can use a right-hand rule for that. Now, if Q is negative, then the force is opposite to V cross B. Now, another way I could do that is instead of using a right-hand rule, use a left-hand rule for electrons. And I was always told never, never, never introduce any left-hand rules because it will just confuse you, but I think it works. And so here we go. Here's a magnetic field region, and the magnetic field, it's all these X's, so the magnetic field is oriented into the page, and a positive charge these are not coming through at the same time. So let's ignore the electrons. Let's look at the protons coming through. So here come a bunch of protons. And the protons have a velocity in the forward direction, magnetic field, oh, here's my diagram, velocity in the forward direction, magnetic field into the board. That means my palm is facing upwards. The protons are going to experience a force in the upwards direction. Now, since they're already moving, that's going to result in circular motion. If it was just sitting there, then it would start accelerating, or it would start having a velocity in that direction. But since it's already moving, a force in that direction does create an acceleration here, but that will result in circular motion. Now, if the particle coming in, let's get rid of the protons and bring in the electrons. If the electrons come in, they have opposite charges on them, so I can use a left-hand rule for negatively charged particles such as electrons. And following that formula, the force there is going to be downwards. So I send through a whole series of protons, and they follow a circular path in this direction. I send through a bunch of electrons, they form a circular path in the opposite direction. And here's the example. So, okay. Is this the problem they gave us? Okay, seems fine. So what we're saying is that oh, how large is the magnetic field? I was trying to figure out what we're solving for here. So what they're saying is that the protons come through, they experience a force of 8 times 10 to the minus 14 newtons. That's a really tiny force. And they're coming in at 5 million meters per second. That's pretty good speed. And a proton has a charge of 1.6 10 to the minus 19 coulombs. So the formula here would be FQVB sine theta. But the way we've oriented this, once again, theta is equal to 0. oh, I'm sorry, if theta is equal to 0, the force would be 0. But what we have set up is the force, or theta is equal to 90. So this is, again, it's the largest force we could get when the velocity and the magnetic field are oriented at 90 degrees. And so solving into our formula, B is equal to F over QV, the sine theta factor dropped out, and this becomes a magnetic field of 0.100 Tesla. You know, this seems like it's a problem that they gave us. I'm wondering if I got this out of order. I apologize. We'll see. It may turn up. Okay. Anyway, what they've shown here is that, let's see, the magnetic field is in the north direction. The velocity is in the up direction. It's a bunch of protons. And what we're showing is that the force then will be in the west direction. Okay, and we'll watch for that to see if that problem shows up in our slides later on. I may have to move around some of these slides. Let's see, here's another example. It says, what would happen if we have a magnetic field? Now what they're saying is we're going to take something that has a negative charge to it near a magnet. A negative charge, negative Q, is placed at rest near a magnet. Now the idea here is that the magnet will be surrounded by a magnetic field. The magnet will be generating a magnetic field. And so the question is, if I take a negative charge and just place it at rest in a magnetic field, will it experience a force? And if it's truly at rest, and it's not spinning, then yeah, there won't be any force acting on it at all. So it won't experience a force. In order to experience a force, the charge that we place in the magnetic field has to have some kind of motion going on. It's either got to go, you know, like in a linear direction, or it's got to be spinning. It's got to be one of those. It's got to have some velocity or some acceleration, or be spinning, which is some velocity or some acceleration. If it truly is, truly just at rest, and it doesn't have any spin, then it won't feel a force. Now, that would not be true for an electron, because an electron does have spin. The electron always has angular momentum, so we can't treat it as if, we could say the electron is at rest, but we also would have to require that it has no spin, no angular momentum, in order to not feel the effect. A positive charge, same thing. If it's a positive charge and it doesn't have any angular momentum to it and it's at rest, no force that it's going to experience. Here I found our missing problem. So here it is. I'll get that moved in the slides. So the magnetic force on a proton and the magnetic field and the force is toward the west. The magnetic field exerts a force. Okay, so the proton is moving vertically upwards. That's what we had in our diagram at 5 million meters per second, and the magnetic field exerts a force of 8 times 10 to the minus 14 newtons, and the force is to the west. Oh, there's the picture. Okay, so here is the problem. And there is the solution. Just a couple slides back. It was close. All right, so I guess we can move on then. So going back to this picture here, where we said, hey, if I have a charge and it enters a region of magnetic field perpendicularly that's uniform, it's going to go into circular motion. So we could actually go in and ask, what's the radius of the circular motion? So here's a good picture. Here's a magnetic field. This magnetic field is into the page, so those X's are saying it's into the page, and then, let's see, it's negatively charged. Is that what they're saying? So this is, charged particles more perfect. Yeah, so I'm going to use a left-hand rule. That's the direction, see my thumb? That's in the direction of the velocity. My fingers are in the direction of the magnetic field, and so the force is where my palm is facing, and my palm is facing this direction. And so what happens is based on what the velocity already is, it's going to have some radius to this circular motion. Now, we need to go in and figure out how can we solve for the radius? How can we predict what the radius of the circular motion is going to be for this charged particle? So it is an electron. That's going to tell us what the charge is. Okay, here we go. Electron's path in a uniform magnetic field. So they're saying that the electron speed, this was the picture, the electron speed is going to be 20 million meters per second, and the magnetic field is going to be just 1/100th of a Tesla, not very much. Oh, it says describe the path quantitatively. Oh, come on, we can go in and calculate for this, so let's do it. So what will that circular motion look like? Okay, now I've solved here for a proton, not the electron, but I felt like it was time. Let's put some numbers in and see what we get. So whether it's positive or negative, what we can say is that we're going to end up in circular motion. The acceleration is given by v squared over r. That's an equation of motion. And then the acceleration will be due to a force, and we can calculate the acceleration by finding the force and dividing by the mass. Now the force for magnetic effects will be QVB. Now there's a sign of theta here, but we've oriented in the picture so that theta is going to be 90 degrees. So we'll ignore that factor because we're at 90 degrees. So the force will be given by QVB over m. That means we can take the kinematic equation, v squared over r, and set it equal to the force equation, QVB over m. Solve for v. V is going to be given by QVR over m. And then finally, solve for r. So I'm going to go ahead and solve for r. This is what the radius of that circle will be determined by. The radius will be determined by the mass, the velocity, divided by the charge, divided by the magnetic field. Now when we think about that, the stuff in the numerator, if the object coming in, see that Q over there, if that object coming in is has more mass or more velocity, the circles are going to be bigger, right? If it's going really fast, it's going to be more difficult to redirect its motion. So more mass and more velocity, I'm going to say makes sense that that's going to give us bigger circles. What would give us smaller circles is if we have more force, and that larger force will come as a result of more charge or stronger magnetic field. So I guess I made these numbers up. The charge here, I put in the charge of a proton, but you know the charge of a proton and charge of an electron? They're the same thing. Now, the velocity coming in is at 20 million meters per second, so that actually sounds familiar. The magnetic field here is 1 Tesla, and then the mass of a proton is 1.67 10 to the minus 27. Now, the charge on the proton is the same as the charge on the electron, but their masses are not similar at all. The electron's mass, or the proton's mass, is 1,800 times larger. So if they both come in with the same V, and they both have the same charge, and they're in the same magnetic field, the radius of the proton's circle in circular motion is going to be bigger by 1,800 times. So we could have these electrons making these little tiny circles and these protons making really, really big circles as a result. So what I ended up with this set of numbers is that the R value for the circular motion is 20.9 centimeters. Okay. They did say electron. Okay. I don't know why I turned it into a proton, but I did. That was the numbers, huh? Okay. All right, go back and see. So the electron is going to be the very same set of numbers, except the mass will be 1,800 times smaller, so the radius will be 1,800 times smaller, And that's going to put it down to where we can't really see it. It's going to be much smaller than a millimeter. It's going to be, you know, in the tens or hundreds of microns. It's going to be circling around the size of, I know I always say red blood cell, but red blood cells are what, 3-4 microns across? So it's going to be circling around the size of a cell. It's going to be really, really tiny circles. Okay, can we stop a charged particle using a magnetic field the way that we did when we used electric fields? And the answer is no, it's not going to be that simple. Notice that if the particle coming in, if we ignore spin effects of the particle coming in, when it runs into the magnetic field is just going to redirect its motion. It's not going to speed it up, it's not going to slow it down, it's just going to end up redirecting its motion if it's a single isolated charge. Now, if it's a group of charge, if it's a bunch of current or something, then we can find ways to slow it down. But a single point charge, a single charge particle with no spin cannot be stopped by a magnetic field. I know that's a dangerous statement to make, but I think that's true. So let's take a look here and see. It says, problem solving, magnetic fields, things to remember. The magnetic force is perpendicular to the velocity and perpendicular to the magnetic field directions. The right-hand rule is useful. I'm going to say it's essential. There's really no other way we're going to end up. We need some kind of a coordinate system to tell us how the vectors are oriented. Equations in this chapter give, okay, right. So we're separating out the calculation of magnitude and direction. Here are some of those examples of right-hand rules. You can refer back to this, but I'm going to say the ones we've looked at are the important ones. Now here's another conceptual example that we can take a look at. What would happen if I've got a magnetic field region? What we said before was if I have a charged particle and it comes into a magnetic field region and the magnetic field region is uniform, that particle is going to get caught in circular motion, right? It'll just keep following the same circle. But that's only going to happen if the charged particle coming in is perpendicular to the magnetic field direction. What if the charged particle is coming in not perpendicular but tipped a little bit? Well, the perpendicular part of the velocity will give us circular motion. So we're going to go into circles. But the parallel component of the velocity means that as the particle is going through circles, it continues to drift in that direction along the direction of the magnetic field lines. So what that means is wherever we have magnetic field lines, if we start firing these charged particles in there, we fire in a bunch of electrons, we fire in a bunch of protons, we fire in a bunch of neutrons, right? Neutrons do have magnetic effect, but electrons and protons. Let's stick with electrons and protons right now. The neutrons don't have a net charge, and so it's not going to be as simple with the neutrons. There, we would have to look at magnetic dipole effects. So let's just stick with the electrons and the protons. What that's going to create for us is a spiral path. So electrons or protons. Now, the electrons and protons would spiral in opposite directions, right? Which would be pretty cool. Any examples of that? Oh yeah, auroras. So again, from right now, from last week, there were some major solar flares on the sun, which end up ejecting lots of electrons and protons out into the solar system. And Earth, fortunately, has a magnetic field. And a magnetic field of the Earth redirects those charged protons and electrons so that they follow Earth's magnetic field lines, and it directs them away from the mid-latitudes and the equator regions, and then most of those charged particles are going to enter through the Earth's atmosphere in the polar regions. All right. And I'm not sure how many of those actually reach the surface. But in any case, here are all these charged electrons and protons coming through. And as they come through Earth's atmosphere, they run into molecules of oxygen and nitrogen and such, and they generate photons of light. So they light up, and that's the aurora. Kind of remarkable. Now, what about the neutrons? It seems like the neutrons might be able to sail right through. Turns out that neutrons are not stable particles. Now, neutrons are stable when they're built into a nucleus with other protons and neutrons around, but a neutron left to itself undergoes decay, turns into a proton, electron, and a neutrino within about 15 minutes. So neutrons that could possibly be coming off of the sun aren't going fast enough to reach Earth in 15 minutes. They decay before they get here. So that's a good thing too. We don't want to be exposed to a bunch of neutrons coming in from the sun. Anyway, interesting application of magnetic forces. All right, so we've got forces on charges. Let's see. So here's a charge coming through a magnetic field region. Now the magnetic field region, if this charge is positive, that's going to direct it curved up, and if it's negative, it's going to be directed curved down. How could we stop that from happening? Oh, let's put in some parallel plates that are charged. So this is taking us back now to chapter 21, 22 and 23, when we were looking at electric forces and electric fields. Is there a way we could get the electric forces to exactly balance the magnetic forces so that the charge could just go right through? And it turns out, yeah, we can do that. We just need to have the electric field oriented perpendicular to the magnetic field. If we have the electric field tipped perpendicular to the magnetic field, then what will happen is the electric field will exert a force on positive charges. This would be downwards, and the magnetic field would be upwards. And if we send the charge through at just the right speed, it would be able to get through that region without any net force, and that would mean that it would sail right through. Now, if it's a negative charge coming through, then the electric force would be up and the magnetic force would be down. So this works for positive or negative charges, and it's considered to be a velocity selector. We could send through a whole beam of particles, and if the particles are coming in and they're going too fast, the magnetic force will be larger and the particles will be pulled out of the beam. If we have particles in there that are going too slow, the electric force will be bigger, and these particles will deflect and hit the negative plate. They'll get pulled out of the beam. So the only particles that can make it all the way through, see that little opening over there? That's what we're aiming for. The only particles that are going to be able to go right through and come out the other side are the ones where V times B equals E. So the velocity we would need is given by E over B, I think. So we need a velocity of E divided by B, and that will be the velocity that gets through, and that's the only one. All right, velocity selectors, that's kind of interesting. Let's look at something that's really, really useful. Something like electric motors. Do we use electric motors for anything? Yes, we do. So we have electric motors. We have electric motors running pumps in dishwashers, and we have electric motors in clothes dryers, drying clothes, and washing machine. We have electric motors all over. We have electric motors that are starting our, either operating our car, if our cars are electric, or getting the internal combustion. So there's electric motors all over the place. How would a basic electric motor work? And there are different designs with these. So one of the basic designs with an electric motor is this. Let's first of all create a region of magnetic field. So we're going to get a magnetic field region set up to start with. And then here are all these magnetic field lines. And then what we're going to do is we're going to take a loop of current. Now what's happening is, let's look at this picture right here, because this is the picture that shows where we're going to have the biggest effect. Now to get a motor rotating, what we're looking for is torque. Now torque is going to be equal to force times a lever distance. And so what's happening here is, if the width here is B, what we could do is say when the current's going this direction, that gives me, let's see if I can get my fingers oriented the right way here. The current is going, oh there we go. So the current's going down, and my fingers are going to the right, because that's the magnetic field, and it says the force is coming out of the page. Now when the current loops around and comes back up over here, now the current's going up and my magnetic field is still to the right. Now the force is going into the page. So this part of the loop is being pushed outwards, and this part of the loop is being pushed back behind the board. That's creating a torque. And the lever distance for that torque is 1/2 of B, where B is the width of this loop. Now, the force that we get is going to be proportional to the length, and so that's A. When we combine all those factors together, we find out that a loop of current produces a torque given by NIAB sine of theta, where theta is the orientation between the loop and the magnetic field. Now, the way we define the orientation of that loop of wire is that there is an area vector, and the area vector is coming out of the page. So the area vector, surprisingly, here it is, the area vector is perpendicular to the current loop. And so with that definition, then now we flip things here, and that's good too, because it's very good to be able to look at these in different directions. So here we're kind of doing a side view, watching this thing spin around. Here it's a top view, so we're looking down on the axis, and we're looking down at these loops, and we're seeing this is the force going back into the page, this is the force coming out of the page, and that's where I'm getting the torque. Now the maximum torque is going to be this orientation, where we have the largest lever distances. Notice as the motor rotates, the lever distance is getting less and less. And so as we go around with this very, very simple motor, the torque is going to get larger and then smaller, then larger and smaller, larger and smaller. Now every half turn of the motor, we are going to need to reverse the direction of the current. So if the current just keeps going in the same direction, we can go halfway around, but the forces are going to prevent us from going any farther. So every time it rotates halfway, we switch the direction of the current. Now that's usually done by making contact. This is a little funny. Usually there's contact points here. I think they're going to show some pictures, some better detail. So in any case, by switching the direction of the current every half turn, we can keep the electric motor running. And the formula at the bottom is telling us how much torque we have at each particular orientation. This is my own drawing of what's going on. Oh, I see what this, I got it. So if you remember back, we had defined back in chapter 21, 23, something like that, electric dipoles. And in one of those chapters, I think it was chapter 21, because chapter 21 had everything in it. For those electric dipoles, what we had shown was that there would be a torque on an electric dipole along, the forces would be along the direction of the electric field. So here's the electric field, here's the dipole, and that's a picture of the dipole in the field, and the dipole was Q times D. This is kind of similar. We call this a magnetic dipole. Now, in the electric dipole case, the dipole made perfect sense because you had a plus charge and a minus charge, and you go, oh, that's the dipole. That's what it looks like. In a magnetic case, there is no plus-minus combination. Instead, what there is a loop of current that runs along the circumference of a certain area. So for the magnetic analog, for the analogous problem with magnetic effects, the dipole consists of a current loop with a certain area, and the area vector is defined to be perpendicular. And the symbol we use for that magnetic dipole is mu, and it comes from taking the current, how much current is there, and how large of an area does the current run around. Seems funny, but mathematically it works the same way as the electric dipole, so that's what we call it. So this is called the magnetic dipole, or the magnetic dipole moment, and it depends on how much current, what the area is surrounded by the current, and then if I have multiple loops, I have to include that effect. So if I have 5 loops, or 10 loops, or 20 loops, I got to multiply by that number. Now, once I've defined the dipole, then I can write down formulas the same way I did with electric dipoles, and the formulas work the same way. So a magnetic dipole will have different amounts of potential energy depending on how it's oriented within a magnetic field. The same way that an electric dipole had different amounts of energy depending on how it was oriented in an electric field. So here's an example, example 2711, the torque on a coil. So we have 10 loops, there's 3 amps, here are the numbers, 10 loops, they're circular, they have a diameter of 20 centimeters, which means they have a radius of 10. There's 3 amps running through the loops, so that's kind of the equivalent of 30 amps. And then the coil is placed in a magnetic field of 2 Tesla. What are the largest torques we could end up with? Now when they talk about these 10 loops, what they're saying is that the wiring is thin enough we can treat all 10 loops as if they basically are just run together. So the collection of loops is pretty flat. It's not like it's spiraling out. All 10 loops are run together, packed very closely together, such that we can treat it as just being kind of flat. And so for that, here's where those 10 loops are located. I tried to draw a couple different pictures. I drew one over here. Now the picture I had over here was with the magnetic field going into the board, and if I place the loops in this orientation, this is just pointing out that's an example of no torque at all. Now this picture, in this picture I've changed the magnetic field so it's running from left to right. Now in this picture this is maximum torque, but if I turn it 90 degrees the torque goes away. Okay, so let's see what the diagram looks like here. If I've got current running here and the magnetic field is to the right. So what I've got here is a current up, magnetic field to the right. The force is going into the board, so I wrote X's. Now what I know is as I get closer and closer to that rotational axis, the direction of the current is now mostly running along the direction of the magnetic field, and that won't give me a torque. So the torque that I am getting is, really strong here, lots of contribution here, not much contribution here and here, and then here it goes to 0. And then on the other side, where the current's running oppositely, the force is out of the board. So from this, what we can say is that, so here's one of those dipole formulas. The torque is given by the dipole crossed with the magnetic field. Now, cross products are handy for writing equations down compactly, but what we know from our experience with cross products is what we really want to do is take this and be able to break it down so we can keep track of directions and we can keep track of magnitudes. Now, the magnitude that would go along with this would say that the torque we're going to get depends on how much magnetic dipole we've got, times the magnetic field, times the angle between them. Now, as it rotates, the angle changes. So the magnetic field is to the right. The area vector is coming out of the board. And that comes from a definition of right-handed coordinate systems. So if I had, let's say we have a coordinate system x, y. If x is to the right and y is in this direction, towards the top of the page, then z is coming out of the page, and that's a positive direction. Well, that becomes the direction for the area vector. So here's my area vector that's perpendicular. And these two vectors right now are at 90 degrees. That's going to give me maximum torque. Okay, so B is to the right, area is coming out of the page. A cross B is going to give me a torque that's vertical. And if you remember from chapters 10 and 11, back in Physics 3A, a torque in this direction tends to rotate the object around this axis. So that's what we're ending up with, and that's our electric motor. So the magnitude here, let's see. The magnetic dipole is going to be given by N times I times A. We can substitute that in. And now I'm just putting the numbers in. The area, did I calculate the area somewhere? Here we go. The area is pi r squared, so the area is 0.0314 square meters. Putting all of those numbers together predicts a torque of 1.88 Newton meters. So there you go. That's how we're going to design our electric motor. How many loops does it have? How much current are we running through the wiring? How large is the magnetic field that we've placed that in? And that's going to determine how much torque we have. And as you know, we have electric motors that have a lot of torque. We can generate a lot of torque with electric motors. Okay, I think we're moving along here. One more example we want to look at, the magnetic moment of a hydrogen atom. Now, we talked about atoms and molecules having magnetic effects. We've got to be able to think in terms of the magnetic fields that they generate. The individual electrons and protons and neutrons all generate a magnetic field because of their spin and the charges that they have. Neutrons have quarks inside that are charged. The charges cancel out, but the magnetic field does not. So the neutron does have a magnetic field to it. So we have the magnetic effects from all of those. And then we also have magnetic effects that come about because of the different quantum states of the protons and neutrons, how they're arranged in the nucleus and how the electrons are arranged on the outside. So we have what are called orbital contributions to the magnetic field, and we have spin contributions to the magnetic field. Now, if you guys are familiar with what's called the Bohr model for the atom, the feature of the Bohr model is that it's wrong, it's incorrect, but Niels Bohr, a Danish physicist, was able to make a series of very correct prediction from a very incorrect model, and historically it played an important role. It really got other scientists thinking about quantum mechanics. So anyway, this is the Bohr model of the atom, and we're going to be looking at hydrogen. And for hydrogen, there's one proton and one electron. And Bohr's model was that the electron was in a circular orbit around the nucleus, and that's wrong. Okay, so it's an incorrect model. My grandma's Danish, and still Niels Bohr was wrong. So anyway, what Bohr assumed was that the angular momentum, m times v times r, needed to be equal to something called Planck's constant. And by starting from this assumption, Bohr was able to make a series of predictions which worked out pretty well. One of the predictions was that the radius of the orbit for the electron would be 52.9 picometers. That was just the right orbit to get this much angular momentum. That is about the size of a hydrogen atom. That's a pretty good number. That's a very usable number in terms of the size of the hydrogen atom. So the model did predict correctly the size of atoms. Now, what Bohr said was, look, there's an attractive force between the neutrons, the electrons and the protons, given by kq1, q2 over r squared. He read chapter 21, so he knew about this equation. The two charges are each a fundamental charge, 1.60 10 to the minus 19 coulombs. So you can calculate the force. So with this radius in place, we can calculate and say, how much force is holding the proton and electron together? Well, in the Bohr model, that would have been, if the Bohr model were correct, 8.2 10 to the minus 17 newtons of force. Now, the electron in the Bohr model, the incorrect Bohr model, is in circular motion. And so the acceleration, the centripetal acceleration, would be F divided by m. This is the mass of the electron, 9.11 10 to the minus 31 kilograms. That gives us an enormous acceleration, 9 times 10 to the 22 meters per second squared. I can use the equation of circular motion to solve for the speed, plugging in the acceleration and the radius. The Bohr model predicted that the electrons would be moving at 2.2 million meters per second. And then we could calculate, well, how much time does it take for the electron to complete one orbit? That would be 2 pi r divided by speed. That's the circumference of the orbit. That's distance divided by velocity gives us time. And it said that the electron was completing an orbit every 1.52 times 10 to the minus 16 seconds. Now, where does this start applying to chapter 27? And what we can do is say, you know, because of the orbital motion of the electron, that's going to create a magnetic dipole. There's going to be a magnetic field generated because of the motion of the electron. And so what we can do is say, aha, there is a current being generated. Current is charge over time. So the charge on the electron is E, and the amount of time it takes to go around once is its period. And so I can calculate I by taking E over T. Oh, I didn't. What was time? Let's see, E is like 10 to the minus 19, and this is 10 to the minus. So the current of the electron is like a milliamp. Okay, so it's not an enormous number in terms of amps, but still, it's just one little tiny electron. So it's producing somewhere around a milliamp, and then the cross-section of the area, the area enclosed by the electron's motion would be pi r squared. So Bohr predicted that hydrogen atoms should have a magnetic field, and that the magnetic field would be given by, well, using our equation for, where did our equation go? Oh, right here, sorry. The magnetic moment, or the magnetic dipole, would be I times A, and Bohr was able to calculate that at 9.27 10 to the minus 24 joules per Tesla, and you know what? That's the magnetic field of hydrogen. Now, how did Bohr get that right? What's the reality behind this? Because this model is wrong. The electrons are not following circular trajectories inside atoms. We'll see several weeks from now. It's based on quantum physics and probability functions and things. But what we believe to be the true story now is that the electron and the proton each have spin. And what we were measuring, this value that Bohr measured and attributed to orbital motion, is actually the amount of magnetic field that's generated by the spin of the electron. So we just need the spin of the electron to be able to come up with that particular value. Now, it is true, when you get out to some of these different quantum states for the electron, that there is an orbital effect. It's not literally following a trajectory, but there is an orbital effect for magnetic fields. But in the ground state, in just a hydrogen atom that's sitting there with the electron in the lowest quantum state, there is no orbital angular momentum. And so there is no magnetic field contribution from the electron's wave function. We'll talk about this in later chapters. Don't worry about it now. If you've taken chemistry or something, some of this stuff may sound kind of familiar. If not, that's fine. We'll get to talking about this later. But it is kind of interesting that Bohr came up with the right size of the atom. He actually predicted the correct energies of the quantum states, and he actually predicted a magnetic field which matched what researchers were able to go in and measure for hydrogen. And all of those were correctly predicted based on incorrect assumptions. So that's a good skill to have, right? Start with a series of incorrect assumptions and an incorrect model, and come up with a series of successful predictions. All right, so I think the rest of this is, here is our electric motor. Here is that close-up I was promising. So here's the electric motor. Here's the magnetic field being generated. This is the north side, the south side. We're generating a magnetic field that passes through. And then there's a bunch of wires here, not just 10 loops or 20 or 30. There could be hundreds or thousands of loops of wire. And then there are contacts, our brushes, along here that are maintaining the current. Now, another kind of electric motor that you may have heard of is an induction motor. And for an induction motor, we can actually we can alternate the magnetic field. So instead of having the magnetic field kind of static and spinning the motor inside there with current, what we can do is we can create a rotating magnetic field which will actually induce a current. So we don't have to have any electrical contacts at all. We can just take an electrical conductive material, place it in there, and we can set that into motion through a process called induction, which we also will chapter 29 maybe, we'll get to looking and seeing what induction is. So anyway, different designs on different electric motors. Here is a speaker. So here's a speaker on my stereo system, and I'm running electrical wires out. How are those electrical wires generating a sound? So here's the speaker, and here is the diaphragm material of the speaker. And you can see that the diaphragm has some of these contacts that are set down inside a magnet. Now when the current comes in and loops around. So they're showing these as a series of current loops. And if a current comes in, then it'll be passing through a magnetic field, and that will cause, depending on the direction of the current, the speaker diaphragm to get pulled closer or pushed away. And so what we can do is we can drive that diaphragm back and forth by sending in a varying current. So that current is going to have the variations of whatever it is we're listening to encoded in the current. It's kind of remarkable that this can be done. You think of the resolution of the sound coming out of a good stereo system, all those details that you can hear, and all those different pitches, all those different frequencies can be controlled by carefully controlling the pattern of current going into the speakers. And then there are those really nice magnets, and if we can match the vibrations of the diaphragm on the speaker, that's going to generate a sound that faithfully reproduces what has been recorded. So another really good application. Now here, this is actually our last example, I think. How are we doing on time? So there are these devices called mass spectrometers. And mass spectrometers can take a series of different charged particles. We're good on time. We've got a bit of time here. They can take charged particles, and what we can do is, now this has velocity selected the particles. Mass spectrometers don't necessarily have to have that part, but we can just take a series of charged particles that have been accelerated, send them into a magnetic field. Now, in the magnetic field, those charged particles will curve, and depending on what the mass is, and depending on what their velocity is, and depending on the strength of the magnetic field, the radius of that trajectory will differ. If there's more mass and more velocity, it will be a larger radius. If it's a larger charge or larger magnetic field, the radius gets smaller. So we can set up a series of detectors. We can send in a bunch of molecules. So let's say we have a bunch of molecules of some compound, we've generated it, we want to find out what its molar mass is. We want to find out how much mass is in this new compound that we've generated. So we can vaporize the compound, create individual molecules, and then we can ionize it by sending it into a high voltage region, and we can pull off an electron. And that gives us a little bit of a positive charge. And so as it goes into the magnets, we got this right. Magnetic field is coming out, I think that's right. So the positively charged molecules come around, and again, depending on where they hit, we can determine what the mass, the molar mass of those molecules are. So let's take a look at an example. In our example, it says that we've got some carbon mixed in with another element that's unknown. So we have some, maybe it's a solid, and we know that it's some mixture, maybe it looks like graphite, but we suspect that it's not purely carbon, that some other element has been mixed into the graphite material or whatever it is. So we can vaporize this, we can send it through the magnetic field, and what it says is in the spectrometer with a magnetic field given by B, the carbon ends up with a radius of 22.4. So we get a large peak. When we look at the output from the spectrometer, we're seeing that the carbon atoms, the carbon-12 atoms, are landing right here, the carbon with a mass of 12. Now there's other isotopes of carbon. Carbon also there's a small amount of carbon-13 present in all of our surrounding carbon, and isotopes 12 and 13 are both stable. And then there's an unstable isotope. There's a radioactive isotope, carbon-14, but that's at really, really low concentration. Anyway, there's 3 different isotopes of carbon. They told us that they think it's a different element. So let's see what we end up with. So what we can do to solve for this is I reverse the magnetic field, so I reverse the directions here, and I put my detectors over here. I didn't make it go through a half circle. I figured we could come up with a radius either way. Now the radius formula we solved before was mv over qb. What they seem to be assuming is that somehow the velocities of everybody coming through are the same. I decided not to make the oh, I see. Okay, yeah, let's move over here. I did this 2 different ways. So first of all, I used their assumption and said if there's a velocity selector, the velocity selector is going to make sure that all the ions coming through are moving at the same speed. Now if that's the case, then I can do ratios and say R2 over R1, the radius of compound of element 2, divided by the radius for element 1, will equal M2 over M1 because, hey, they're in the same magnetic field, they've both been singly charged, so all the molecules, or most of the molecules, end up losing 1 electron and becoming singly charged. And then the velocities too will cancel out because we have velocity selected them. If that's the case, then what we can say is this. So that results in saying that the mass of 2 is equal to the mass of 1 times the ratio of R2 to R1, and they gave us those numbers, and they're on the previous page. So the numbers here are 22.4 centimeters and 26.2. So putting those numbers in, assuming that they've been velocity selected, so the ions are coming through at the same velocity, that would say that the mystery element has a mass of 14. Now 14 would be nitrogen, by far the most abundant isotope. Are there any other isotopes of nitrogen that are stable? 14 is definitely stable and the largest component of naturally occurring nitrogen. So anyway, it could be there's a little nitrogen inside. Now the other way to solve this is to say we don't use a velocity selector, but all of the particles are going to come out with the same kinetic energy. So the kinetic energy is going to depend on the voltage that was used to accelerate the particles. So this makes it a little more complicated because if they come through with the same kinetic energy, then I have to substitute in 1/2 mv squared as the kinetic energy and then solve for v. So v in this becomes equal to speed does depend on the voltage. Now they both have the same voltage. Depends on the charge. They all have the same charge, but it has a mass dependence. So if they come through with the same kinetic energy, then I have to write this formula down. I take out the v and replace it with the charge and the mass and the velocity. And this says that the radius is proportional not directly to the mass, but mass to the 1/2 power. So the ratio here is, for the two elements, R2 over R1 is proportional to M2 over M1 square root. Now if I put those numbers in, it says that the mass that came through is at 16.4. 16.4 is not a good number. Any atom that shows up should have an integer number of protons and neutrons, so 16.4 doesn't work. It's kind of halfway between a mass of 16 and a mass of 17. So, I mean, they intended for us to do the simpler approach, and that's the one that gives us an answer that's actually an integer. All right, I better wrap things up right there. I think we are out of time. There's a good bunch of formulas here at the end in the summaries. Sure, we could end on the mass spectrometer, or we could end on the calculations that we did. All right, so questions, let me know. I know these are moderately challenging chapters, so certainly keep track of all the three-dimensional stuff. So stop by office hours and let's get your questions looked at.